In this presentation, we look at the binomial theorem. The classic factorial function is needed for the binomial theorem. That is that n factorial is defined to be n times n minus 1 times n minus 2 and so on down to 2 times 1. It's the product of all the integers as I goes from 1 to n. So we'll start at n, go down to 1. So for example, 3 factorial would be 3 times 2 times 1. 4 factorial will be 4 times 3 times 2 times 1, and so on. The number of ways to choose R objects from a set of n is described with the following notation. It's the binomial coefficient n choose R, and it's defined to be n factorial divided by R factorial times n minus R factorial. It is also sometimes written as CNR instead of n choose R. But we're going to call this notation n choose R here. The combination of n objects taken r at a time is a binomial coefficient, and it can be computed by what is often called Pascal's triangle. Although Indian, Chinese, and Arabic mathematicians knew of Pascal's triangle 500 years before Pascal. We can do computations like n choose r, the number of combinations of r things taken from a set of size n, from smaller values by Pascal's recursion. This is a theorem. N choose r is the same as the sum of n minus 1 choose r plus n minus 1 choose r minus 1. N choose r is equal to the sum of n minus 1 choose r plus n minus 1 choose r minus 1. If you're picking R people from a group of size n, you can either leave somebody out and choose R people from a set of size n minus 1, or you can include that person and choose the R minus 1 remaining people from the remaining n minus 1. We can prove this by simple algebra. We can write out the various binomial coefficients with their factorials, and on the right side get a common denominator and simplify. This expression, after we put in the factorials and simplify, nicely turns into this, and it's a fun little algebra problem. I thought it was fun. Pascal's recursion gives a nice way to compute the various binomial coefficients for small values. What we do is we start with n equals 0 and then increase the value of n. So we create a triangle like this. On the left side, coming down the triangle, is 1 choose 0, 2 choose 0, and so on. On the right side, going down the triangle, is n choose n. These values will be 1, and Pascal's recursion allows us to find the items in the middle. We'll go through this. N choose 0 and n choose n are 1. The number of ways to choose nothing from a set of size n, or the number of ways to choose everything from a set of size n, is just 1. These will be the boundaries of our triangle, and then Pascal's recursion tells us how to get any binomial coefficient that's in the interior of the triangle, and we do that by taking the sum of the things on its shoulder. So for example, here are the first few rows of the triangle. Again, notice that the ones come down the left side, the ones come down the right side, and anything in the interior is the sum of the things above it. So this 2 here is the sum of the ones above it. This 3 down here is the sum of the 1 and the 2 above it, and so on. Let's work through these first few rows. Again, we start with this. The ones are getting ready to go down the left and right side, and the next row will have a 2 in the middle. This 2 is the sum of the ones above it. And then there's a 3 in the next row. This is the sum of these things, the 1 and the 2 above it. This 3 is the sum of the 2 and 1 above it. As we go on, a 4 is the sum of the 1 and the 3. The 6 is the sum of the 3's, and so on. The so-called fifth row, I'm going to think of the top as being the 0th row. The so-called fifth row has a 1, 5, 4 plus 6 is 10. 6 plus 4 is 10, 5, 1. The next row, 1, 6, 15, 20, and so on. 7th row, 8th row. This is exciting. There is the first 15 rows or so, with the odd numbers here are in orange and the even numbers in blue. So the even and odd numbers make an interesting pattern. There are all sorts of fascinating patterns that show up in Pascal's triangle. And this copy of Pascal's triangle I got online using the Creative Commons Attribution license, so I'm thankful to Paul Gaborit for setting this up. The binomial coefficients are the coefficients in the expansion of x plus y to the n. N choose r will show up somewhere when we expand x plus y to the n. The sum x plus y is called a binomial, meaning two terms. And so for this reason, these expressions are called binomial coefficients. And the binomial theorem states this explicitly. The binomial theorem says that if you give me a natural number like 5 or 7 or 23, x plus y to the n is a sum involving the binomial coefficients and powers of x and y. X will essentially decrease in power while y increases. As an example, x plus y to the fifth can be computed using the fifth row of the triangle, 1, 5, 10, 10, 5, 1. So x plus y to the fifth, what I'm going to do is I'm going to write down powers of x and y. X to the fifth, y to the 0, x to the fourth, y 1, x cubed, y squared, y cubed, and so on. And the coefficients that you see here, 1, 5, 10, 10, 5, 1, come out of the triangle. I can clean that up a little bit. Again, where did this come from? You see the red coefficients 1, 5, 10, 10, 5, 1 come out of the row of Pascal's triangle. The binomial theorem, or Pascal's triangle, lets us expand powers of x plus y, and we will need that in a number of places in our course. An immediate place is to compute the derivative of some power of x, and this is a good tool for us to have.